Welcome to your Albatross UAV flight test briefing. One of the preliminary tests that must be carried out is a weight and balance test. This first verifies the mass and CG positions from measurements of the wheel reaction forces by measuring the moment arm of the port starboard nose gear, then using the respective loads to calculate the CG position. This will help you to determine the handling properties based on ground handling and the management of load within the aircraft. To ensure that the aircraft performs as expected, the CG must always be forward of the center of lift to avoid static instability. If the CG is too far in either direction, the aircraft cannot be controlled in pitch and the control surface inputs would be less effective. By increasing the static margin, the aircraft will become more stable but less maneuverable. We need to determine the sensible aft CG limit, which will ensure that the aircraft can be trimmed and maintains margin for maneuvering. For now, we will select 35% of the Mach, which places the CG at about 0.0815 meters aft of the datum point, which is the leading edge of the Mach. We will now check the flight controls and assess the input and output for the required aircraft motion. The elevator controls in this aircraft need to be reversed. The ailerons also need to be reversed to provide a roll right and roll left response. The rudder should provide a yawing motion in the left and right directions. This verifies that the side slip has the correct sign. The deployment of the flaps should be checked in the up and down direction, and finally, the throttle up and throttle down should be checked as well. The thrust test revealed that this aircraft produces a steady linear acceleration with increasing throttle input to a maximum thrust of 29 newtons. The longitudinal pitching motion is highly dependent on the free stream speed and CG position. To assess the pitching qualities of this aircraft, a variety of wind speeds were tested to assess the change in response to elevator input. At a speed of 15 meters per second, the time to subside is 2.7 seconds, resulting in a damping ratio of 0.292. But how is this relevant? If we compare this to the same test at wind speed of 20 meters per second, the time to subside is 1.1 seconds and the damping ratio is 0.367. At a speed of 40 meters per second, the time to subside is 0.6 seconds, resulting in a damping ratio of 0.671. This means that at higher wind speeds the aircraft is more responsive to elevator input and reaches the stable angle of attacks faster. The short period shows how the aircraft responds to sudden changes in pitch. Here the damping ratio is 0.531. The CG should be optimally placed to allow for reasonable amount of elevator input to produce acceptable pitch control. Here it is shown as CG of 10% Mach even with maximum control input leads to a limit of 9 degrees of angle of attack. On the other hand, a CG of 30% Mach with maximum elevator input leads a maximum stable angle of attack at 12 degrees with a reasonable amount of elevator input. For this reason, CG position for pitch control to be maintained is recommended at about 30 to 35% of the mean aerodynamic chord. The steady roll rate increases with increasing free stream velocity. As such, the aircraft will feel more responsive to roll inputs at higher free stream velocities. The damping in response to rudder input is less in comparison to the elevator input. The time to subside and reach steady state is about 5 times faster in pitch than in yaw. As the CG vertical position is increased, a larger nose-up pitching moment is induced. Similarly, as the vertical position decreases towards the belly of the aircraft, there is a large nose-down pitching moment which can lead to premature stall. The zero pitching moment is parallel to the prop shaft and is at approximately minus 0.05 meters from the reference point, where there is minimal change in the angle of attack when thrust is applied. Here the coefficient of lift against angle of attack is shown for different flap settings. If you apply more flap input, lift coefficient increases. The maximum lift coefficient is 1.2 and occurs at an angle of attack of 16 degrees for the given aircraft configuration with a flap deflection of 40 degrees. This is slightly below the manufacturer's quoted value of 1.4. The trade-off between lift and drag for the entire flight envelope can be seen here in the drag polar for a variety of different flap settings. For this aircraft, the best predicted L/D is 15 for a flap deflection of 40 degrees. This occurs at a lift coefficient of 0.6. Here the required coefficient of lift for trim is shown at the given elevator deflections. The coefficient of lift to maintain trim increases with elevator deflection. this graph we can see how the CG positions affect stability. As you can see, moving the CG towards the nose of the aircraft, denoted by the line in yellow, results in a more stable aircraft configuration. As the CG is moved backwards, the configuration is less stable. The gradient of the linear section of the 35% CG position is essentially flat. This tells us that this is the upper aft CG limit for stability. The aircraft responds well to rudder inputs when maneuvering on the ground. As speed increases towards 10 meters per second, the rudder control results in a greater angular acceleration of the aircraft, which sometimes results in the wingtips dropping towards the ground, and the aircraft velocity vector is no longer aligned with the wheels, which results in the aircraft drifting. As a result, it is recommended that the aircraft maintains a slower speed at maximum of 6 meters per second when taxiing. Having performed multiple takeoff procedures, the aircraft takeoff speed is around 18 meters per second at a weight of 69 newtons without flaps deployed. When flaps are deployed, the takeoff speed decreases to around 17 meters per second. At a cruise speed of 23 meters per second and altitude of 225, the throttle was set to 15 RPM and the elevator trim set at -3.3 degrees. The lowest speed at which the aircraft can maintain approximately steady level flight is 15 meters per second at around 200 meters altitude. The highest speed achieved in steady level flight was 68 meters per second at an altitude of around 620 meters. The phugoid mode is an aircraft motion in which the vehicle pitches up and climbs and then pitches down and descends, accompanied by speeding up and slowing down as it goes downhill and uphill. The phugoid mode is characterized by the damping ratio and natural frequency of the motion. For this aircraft, the measured damping ratio was approximately 0.124 and the natural frequency was 0.571 radians per second, with a time to subside of approximately 2 minutes. The aircraft CG is located at 30% of the main aerodynamic chord as described earlier, which means that it is damped so that it will eventually reach steady state. Now that we know more about the aircraft, we can finally take it for its first flight test circuit around the pylons.